Let us look at the first order and second order global sea level cycles and how they can be linked with anything else. Let us take the geological time, millions of years. This is 500 million year and this is the present day 0. The sea level curve is shown by the solid line and the ocean crust accretion is shown by the dashed line. We observe when the accretion is reduced, the sea level is reduced. When the accretion is high, the sea level was high. For example, here the sea level has fallen, and indeed here also the oceanic crust accretion is reduced. Then when the oceanic crust accretion has got increased, not exactly at the same time, but subsequently we find an increase in the sea level, and then when the oceanic crust accretion got reduced, then the sea level also fell down. So we can find a proportional relation approximately between the oceanic crust accretion and sea level. Now, along with these curves, one can compare the global tectonic cycle. Breakup of late Proterozoic supercontinent was happening here. We note that the oceanic crust accretion has gone to this direction when there is a breakup happening. Here is a breakup happening and here the curve goes down, and whenever there is a dispersal, here is a maximum dispersal of continents and here is a dispersal of continent once again, we find there is a rise in the sea level. Here is a maximum dispersal and in this place is nearly plateau. Now, if you look at the second order cycles or the super cycles, the curve links more efficiently with the global tectonic cycle. Nearly when the maximum dispersal of continents happen, the global sea level falls. Whenever there is a breakup happening, there is a sea level fall. When there is a rifting taking place, there is a sea level fall, not exactly at the same time, but at a comparable time. At least in one ice house time, we are finding a sea level fall, and then when the ice house time is ending and the greenhouse time is coming up, there is a sea level rise. To define cycles in the rock record, we need at least two rock types. If the rock type is, say, sandstone and that continues maybe at different times, it may not be possible to distinguish. That is why it is said at least two rock types are required. There can be 3 or 4 also. Complex cycles are easy to recognize by geologists. The reason is the distinguishing features of different units become clearer. There are older literature that discusses about what kind of repetition should be called a cycle. Should it be ABC, ABC, or should it be ABC, BA, BC? The stratification cycles have been loosely called as bundles. This is a new term for the students. 3 kinds of cycles can be thought about. Sequence cycle, where the rock types are varying, say AB, AB in this way. Second is the thickness cycle. Rock unit A is deposited, which is very thick. Then after some time, maybe some other rock type has come, which is B, which is thin. Then a very thick rock C has come, and then a thin rock D has come. So it is variation from thick to thin to thick to thin. This can be called as a thickness cycle. What is time cycle? Say there are rocks A, B, and then C, D. The time gap from A to B and that between B to C are nearly the same, between C and D also nearly the same. So, there is a sequence of rock formation after certain time interval. So, that can be called as a time cycle. What is cyclostratigraphy? This is a branch of stratigraphy that is concerned with the identification, characterization, correlation and interpretation of cyclic variation in these stratigraphic records and their application in geochronology to improve the accuracy and resolution of time stratigraphic frameworks. When we are dealing with rocks with cyclic variation, sometimes we are incorporating geochronologic date. That branch of stratigraphy is called cyclostratigraphy. Is there a relation between the bed thickness and the theoretical sea level? Let us have a look. Here is a sea level curve and here are the bed thicknesses. When there is a sea level high, we are finding thicker sedimentation. I am requesting students to follow the curve and check whether in case of high sea level we are always getting thick deposits or vice versa. Let us look at the different basin margin types. Shelf break margin. This is a case where there is no drastic change in curvature on the slope. There is no drastic change in the slope, but if there is a sharp change, we call it a ramp margin. For example, from here to there is a significant change in slope. Here it is gentle slope, whereas here it is a steep slope. Such margins are known as the ramp margin. When the margin is defined by normal faults, we call it a rift margin. In case of a foreland basin, there can be low angle thrusts, and then there can be topographic difference. From here sediments will come and deposit, and this is known as a foreland basin margin. What happens in case of a growth fault? This is a schematic diagram of a growth fault, which is a listric normal fault. It is non-tectonic fault, also called atectonic. We do not know exactly how it forms in the sediment, but probably due to differential compaction of the sediment, growth faults are produced. For example, in this hanging wall block portion, suppose there is more compaction, then this block will move down compared to this block. Such folds within the hanging wall block is known as rollover anticline, can be a potential site for hydrocarbon accumulation. Therefore, this can be a potential site of drilling. Now, these growth faults actually can keep producing new splays. These are known as the splays. These are the normal faults that join with a master fault at the base. So, in this way, the basin margin can get modified. They are found in the coastal area where there is a sediment supply. Different kinds of structural barriers one can think about near the seaward margins of the continental shelves. For example, this can be a basement ridge, and this is the sea level. This is the shelf area. Basement ridge can be there, or consider of folded rocks, so that this is the sea level, and the sedimentation pattern here and here, the geometries can be different. It can be a faulted block. Basically, one block has gone down with respect to the other. So, there is a deeper ocean, deeper part, and this portion will be the shallower part. There can be a carbonate reef development, and this can be the position of the deeper sea. This can be the place of shallower water. If this reef actually moves up, then it can separate water into two portions. Here then water will become stagnant, and here water will still have movements. Just like a reef, there can be a volcanic ridge developed, and in this way the coastal area is divided into two portions. Just like the volcanic ridge and the reef, there can be a diapier produced due to differential density, and then the low density material is moving upward and then has created such a topography, and then again the coastal area is divided into two parts. This is the deeper portion, and this can be the shallower portion. The sedimentation patterns will be different in these two places. While talking about sequence stratigraphy, we have referred to the shallow water deposits, deep water deposits, and how do we find out based on fossils, ichnofossils, the water depth. Ichnofauna depends on several environmental variables, but can be simplified into scheme based on water depth. The shallow marine environments are of higher energy and are richer in nutrients than the deeper water environment. This is a sentence almost universally true throughout the world. Exception is the lagoon, where is a place of low energy and poorly supplied with nutrient, yet it is of the shallow water. It represents shallow water regime. Even though in lagoon it is a shallow water regime, it is a place of low energy, limited movement of water, and they are poorly supplied with nutrients, mostly cut off from water in other systems. Let us take a coastal area, say this is 200 meter depth and this is 2 kilometer depth. Below this lies the abyssal zone. Between 2000 meters or 2 kilometer and 200 meter lies the bathyal zone, and shallower than 200 meter is called the shelf of the sublittoral zone, and the shell portion in connection with the landmass here on the surface is called the littoral zone. Now, here one can define sandy shore littoral zone, shelf sublittoral zone here, bathyal zone here and the abyssal zone over there. The kind of ichnofossils we get are different. In case of a sandy shore, we get the scolithos assemblage. What are they? They are the vertical burrows, simple U-shaped or pellet lined. These are the examples. In the shelf area, we get Cruziana assemblage. What are they? They are the wide variety of forms, surface tracks and trails, complex networks and different kinds of burrowing can be seen. In the bathyal zone here, we get the zoophycos assemblage. They have limited variety on surface and shallower subsurface. This is the appearance, and in the abyssal zone we get regular patterns seen on the bed surface only. On the bed surface only we get these patterns. So, if we get a scolithos assemblage looking at a very shallow depth regime of littoral zone, still deeper zone will be indicated by the Cruziana assemblage, zoophycos and the bathyal zone and the abyssal zone by this. So, if we get in a vertical rock record a scolithos assemblage and followed by a Cruziana assemblage and then over that is a zoophycos assemblage, that means with time relative water level increased. And consider a vice versa situation, scolithos assemblage at the top, Cruziana assemblage in the middle and the zoophycos assemblage in the bottom. This means with time the relative water level decreased. So, it is a simple presentation how the ichnofossils can be used in understanding the deeper water and the shallower water regimes. Note that the name of assemblages are taken from one particular ichnofossil that may be typical. Example, Cruziana assemblage. Here Cruziana is typical. Bioturbation is a process by which organisms disturb the sediments. Say this is a sedimentary record and then there are organisms which are taking this sediment at the top, and in this way mixing of sediment can happen. This is known as bioturbation. It is common in the shallow marine deposits, and its absence of bioturbation can indicate anoxic condition. A bioturbated sediment, even if I pick up from some horizontal surface and date, the dates can be different because mixing of time has happened. Even if we are picking up the orthogenic minerals. We discussed in this slide how to understand shallower water and deeper water regimes through ichnofossils. Now, we are going to see the rate of sedimentation. Here is an example. For slow rate of sedimentation, sediments on sea floor get consolidated and it is called firm ground condition, and the characteristic ichnofacies is called the glossy fungites. This is an example of the glossy fungites. Well defined burrows are found and we can find some finer fabrics within the sediments. But at even slower rate of sedimentation, a hard ground condition is generated and the characteristic ichnofacies is called the trypanites. This is the hard ground condition and the trypanites are demonstrated. We are going to see the different successions in the coastal environment and in the ocean environment. Let us start with the delta deposits which can form where the rivers meet the seas. This color represents muddy material, this is the sandy material. Let us look at a river dominated delta, a wave dominated delta and a tide dominated delta. In all the cases, one thing is common, that the bottom portion in the pro delta region we find alteration of thick mud unit and thin sand units. Then comes a zone of sand units, the thickness may vary. Note, I am not marking a correlation by drawing these lines, I am just comparing the lithological units, sand dominated units, and over that lies alteration between mud and sand. Now, the individual thickness of the layers in each cases can vary. A tidal channel deposit is thick in case of a tide dominated delta, which is not the case with the wave dominated delta and the river dominated delta. Let us look at a lagoon and how the depositions in vertical succession look like. Here we get thick mud unit and thin sand unit in between. These thin sand unit thicknesses individually can vary. Wave ripples can be produced here. The bioturbated muds can be found in this region. Bioturbation means that there are organisms that mix up mud, leading to a mixing of time. Storm dominated marine deposits are interesting. For that, let us understand what is a hummocky cross stratification. We have discussed about cross stratification in the primary structures related NPTEL lecture. This one, hummocky cross stratification, was not considered. They are the rounded mounds of sand of the sea floor. We can see the rounded mounds, few centimeter high and tens of centimeter across. They are convex upward. We can see the convex upward geometry here, and the dip in all directions are 10 to 20 degree. So, the dip at all directions are 10 to 20 degree. Between hummocks lies the swells. This is a swell or the depression where the layer is concave upward. Sometimes it is also called hummocky swelly cross stratification, and it is a characteristic of storm condition on a shelf. We find such hummocky cross stratification within the storm dominated marine deposit. From bottom up to this one, we get sand and mud alteration, then we find the hummocky cross stratification unit, then swelly cross stratified sands are found, and finally the stratified sands. Tidally influenced shelf succession looks like this. There are sand mud alteration and the sand layer thickness can increase as one goes vertically upward. Sands reworked by tidal currents will be found because it is tidally influenced shelf succession, cross-bedded material sand and then the stratified sand at the top. Let us look at the different submarine fan facies models. The first one is a gravel rich submarine fan. This one, coarse alluvial supply gets deposited on the land and also it continues in the deep sea floor as a single unit. Sand rich submarine fan, here the spread is more vast and the different lobes and sublobes can be seen, which is in contrast in geometry from the gravel rich submarine fan. Since in case of B, sand rich submarine fan, sand is more prone to movement, therefore this detailed geometry is produced. Mixed sand mud submarine fan, here the spread will be more possible because mud is more mobile and we can see the more complicated geometry and more widespread of the material. And finally, the muddy submarine fan. So, the grain size has reduced. We started with gravel rich fan, then we moved to sand rich fan, then sand mud mixture and now completely muddy. Therefore, the flow is more extensive, goes much inside the deep basin and this is shown here. Let us look at the sedimentary logs through submarine fan deposits. There will be an alteration of sand and mud in the inner fan, which means close to the land region. Then there are coarse grain materials in several packages and then comes the sand. Mid fan, which is in deeper water than the inner fan, these coarse grain materials are missing and it is an alteration between mud and sand. In case of a distal fan in the deeper water regime, the clay content, mud content has increased and the sand content has been reduced. They are now occurring as finer layers. Let us look at the ocean currents and the related pelagic sedimentation. Bottom currents construct contourite drifts. These are the large accumulation of sediments distributed in the modern ocean, can be up to 2 km thick, poorly sorted muddy sediments and are intensely bioturbated. They contain thin horizons of fine grained sands and silts. They are terrigenous and sometimes volcanogenic sediments, and they are the products of continuous flow. So, this succession contourite drift is mostly mud and there are few sand or silt layers in between. Pelagic sediment, we come across this term in sedimentology and also in stratigraphy. They are the suspended material that were floating in the ocean away from the shoreline and has settled on the sea floor. Mainly they are clay and some silt sized particles. Microfossils may be there. In case of hemipelagic deposit, what it means? They are the fine grained sediments in the ocean that has been derived from a nearby continent. They consist at least 25% non-biogenic materials. and the consolidated variety can be called as the mud rocks.